overview of the semester. We have another talk in the service, what is the Nobel Prize about? And it turns out that when it comes to Haldane part of the Nobel Prize, it is very hard to find a speaker that can explain what is the Nobel Prize about. I looked around and eventually Assa agreed to take the challenge and to try to explain to us something that I've been trying to understand for the past 25 years. Good luck to you, Assa.
Okay, it is a challenge. You know Duncan Haldane for quite many years. Read quite a lot of his papers, but I know only a very small amount of what he wrote and what he knows. So I try to scrape a little bit of that. And as all these talks are, usually like last talk we heard about Topological by Yossi. Yossi's here?
Yes.
Hi. I'm going to talk about you. Okay, so this is the Nobel Prize this year. As you can see, they split it between two types of works. One is Topological Phases of Matter, David Towles and Duncan, and then the famous Towles. The connection between them is the word topology, but that was essentially, in my opinion, chosen in order to give essentially these people a Nobel Prize because of their life accomplishments. And the life accomplishments of David Towles are very wide, and the same goes for the others. So I'm going to just touch on some of Duncan's work. But before that, I want to clarify some issues that came up from last talk that Yossi gave about David Towles and the Hall effect. And this is actually a figure that came up in Duncan's Nobel talk in Stockholm, where he showed Yossi's famous butterfly that decorates our department everywhere. And he explained that this shows how topological numbers are important in understanding electrons in the magnetic field of the lattice. And he especially thanked Yossi for giving him this nice figure, although he rotated it by 90 degrees, which is a big issue. Yossi doesn't like it this way, he likes it horizontally. But in condensed matter, we usually plot the energy vertically and some other parameters like flux or band or whatever we plot horizontally. So except for that, I want to repeat essentially some stuff that Yossi talked about and make a bit of a clarification. So there is a very famous formula by Towles from automatic aldane that showed that the whole conductivity is essentially the integral over the brilliant zone for lattice models with translational symmetry, and this integral happens to be an integer times e squared over h, and that is essentially what you get for non-interacting electrons on a lattice. Beautifully generalized by Yossi, this expression was actually shown to hold for many body systems, and this is just a special case of a much larger class of problems where there are interactions, there's disorder, and all the assumptions that go into this theory doesn't work, but still the whole conductance is e squared over h times an integer. That integer is called Chern number. So that's very important, and it's very useful actually. I'm using it myself. My students have been using it during the years to calculate whole conductance of interesting models beyond non-interacting electrons. But unfortunately, they do not explain the whole plateaus. Now the whole plateaus, as you remember, are the reason anybody was so amazed by the Hall effect. There were some regions that the whole conductance did not change at all as a function of magnetic field. But whole conductivity, written in another way, is essentially the number of electrons divided by magnetic field if you have no disorder, let's say. And if the number of electrons is not changing, and you're changing magnetic field, the whole coefficient should change. So, or these integers should change. So, in other words, the fact that this quantity happens to be an integer on the totals does not mean that one should get Hall plateaus. So why are there plateaus is a completely different ballgame. Different explanation. It's not the topological aspect that's important, only the topological aspect, sorry, that's important to explain that. Yes?
If it's always an integer with interaction with anything you want, then how come that fractional Hall effect can exist?
What does this say?
That was a theory.
If the Hall conductance is quantized integer, what are these fractions? That's your question, right? Great minds think you like this.
Excellent.
Okay, so it's another issue coming from the Hall effect that the fractional quantum Hall is not explained well. Eventually, people understand it also in terms of the topological quantum numbers, but it's not directly explained by the TKNN or the Yossi's formula. So the question is, how do you understand the Hall effect? And let me give you a very simple explanation. And the reason I'm giving you this explanation is because I want to put my finger on a quantity that was not discussed last colloquium, and it's called incompressibility. And let me explain what that means. So when you take non-interacting electrons on a cylinder and you plot the bands, you have a good quantum number parallel to the cylinder, it's called kx. You get these bands that in the center of the cylinder are essentially separated by the what's called the cyclotron gap. And if you put the chemical potential somewhere, and you get all these filled levels, then in the center you see there's a gap. It's called the bulk gap. But why do I mention a center? Because at the edges, these bands have to go up because there's essentially they float up because outside the cylinder no bands anymore, and they cross the Fermi level. And here you have gapless excitations of particle Hall that are compressible, because when you have low energy excitations and no gap, you can compress the system, you can change the density at small energies. So Hall systems in general have this property that the bulk is incompressible and only the edges are compressible. And that is the reason you get plateaus. So as was explained by Loefflin himself and by Halperin, so you get these plateaus that you can see there, highly quantized. Essentially, I can give you a simple explanation of why it works. Think of a cylinder that is penetrated by a magnetic field from all sides, also from this direction. Put an electron liquid on it, and I tell you that the liquid in the center is incompressible. Here on the edges, it can be compressible, but think of water essentially that you cannot compress. So you have some region which is incompressible. Now, what happens is when you put an Aronoff-Bohm flux in the center and you change as a function of time, you're producing an EMF according to Lenz's law, Faraday law, around the circumference. So you have, if you want, a field in the x direction. And now what will happen is because you have a magnetic field and you change the Aronoff-Bohm flux, all this incompressible liquid is pumped upwards. And when it's pumped, and you can see my animation took me a long time to draw. I do it again because I'm so proud of it. Then you get okay. Then you get pump charge. Now, how much pump charge is exactly given by the density here. The density here will tell you exactly how much pump charge is. It's the density of the bulk. It's not the density here at the edges, which is lower because you're losing states into the across the Fermi level, but it's the bulk density. So the bulk density is what determines the Hall coefficient. And the Hall conductance is now the bulk density, NEC over B. It's not equal to an integer in general, and the plateaus correspond to the fact that the special density of incompressible ground state. So what makes the special values is the special numbers for the bulk density. So the bulk density could be fractional. It could be that n over b is integer, or it could be fractional. And the question is, how come? This was the question that was lying in front of everybody when they discovered the fractional quantum Hall effect. And I was a student at the time in Stony Brook, And I remember one of the teachers, his name was, he gave me the problem of reading the paper of Laughlin and explaining to whoever why this explains the fractional quantum Hall effect. So suffice to say, I wasn't very successful in understanding the paper and explaining the Hall effect. It took a long time until people understood why this many-body wave function has anything to do with plateaus of Hall and fractional numbers. But I'll give you the short story. So it turns out that this many-body wave function happens to have a density which is 1 over an integer number of electrons per flux quantum in the right units, per Landau length, if you want, Landau area, flux quantum. So the Hall coefficient, as I said before, is just a density. So it's e squared out of the density. Now the density is going to be 1 over n times e squared over h. And n is an integer. It happens to be an odd integer, so that this is obeying target principle. Now, why is this an explanation? If you write down the wave function and say, look, I have a wave function with wonderful properties, people will tell you, prove to me that this wave function is a wave function of anything interesting. So Laughlin didn't really do that. He said, it has good energies. If you put Coulomb interacting electrons with a magnetic field, you get good energy. So it's an excellent variational wave function, better than Hartree-Fock. But everything is better than Hartree-Fock, so that's not a good argument. But he said another argument, which was more interesting, a finite gap for charge excitations. And that means incompressibility. That means you cannot change the charge. You have the charge exactly given by 1 over n. You cannot change it without costing energy. This he managed to show. And once you have an incompressible state with a fractional density, you have a fractional quantum Hall. But the question was, why is this wave function good? And to show that it's relevant to anything. So then came Duncan. Now the story of Duncan and Haldane, Duncan and Laughlin is interesting. The paper of Laughlin, there were 2 papers Laughlin wrote. He wrote a paper about the theory of the fractional quantum Hall effect. He sent it to Fisher's letter and it landed on my advisor's desk, Steve Killerson, who said the paper is wrong. He sent it back. Laughlin was very pissed off and took the paper back. And then nobody heard from him for a while. It was a theory of, I don't know, something with crystal, I don't know, some idea like that. He took it back, and he sent this paper. This paper landed on Duncan Haldane's desk. Duncan Haldane looked at this paper, and he told me, within 2 seconds, he said, he got it. And he snatched the theory out of my own hands, because he was working on this problem very, very hard, and the moment he saw this wave function, he said, that's it. Now, that, to me, is a sign of, unusual wisdom. Because not only did he identify that this is the right way, but he proved it. And he proved it by writing the Coulomb Hamiltonian in the lowest Landau level in terms of a trick called pseudopotentials, and proving that the coefficients of the pseudopotentials are positive. And if you truncate this list of pseudopotentials to a number which is actually 2, in the case of nu equal to third, this is the exact ground state of a Hamiltonian. It's not very far from the Coulomb Hamiltonian. And this Hamiltonian has a gap, so you can also show that if you put the real Coulomb Hamiltonian here, you don't truncate it, the remainder that you add is a small perturbation that is controlled by the gap. So once you have a controlled expansion in a gap situation, it's not the most rigorous mathematical physics I know, but it's quite persuasive that you found the answer, because that wave function, as I said, is justified. So he explained why the wave function is justified, and he also got other fractions called the hierarchy of Haldane and Halperin, and other fractions that appear in the experiment. So that was his contribution, for which he did not get the Nobel Prize. The Nobel Prize went to Laughlin, but I want to show you what he got the Nobel Prize for. So the Nobel Prize of Duncan Haldane got for essentially two works that he did on quantum spin systems and on topological insulators. But I do want to list all the rest of the stuff, because all the rest of the stuff is the subject of all these textbooks you see here. There's a Subir Sachdev textbook, there's Giamarchi, there's a famous quantum Hall effect textbook, there's mine, which large parts of each one of these books books is Haldane's theories on all these different subjects. One-dimensional quantum systems, solvable models of spins, exclusion statistics, quantum geometry, and the fractional quantum model I mentioned, but I don't discuss anything else except these two things he got the prize on. So, symmetry breaking, as you know, is very important in back. Okay. Okay, very careful with it. So symmetry breaking, oh, that's not the way I want to show it. Is a system, is a way of describing phases of matter. Not all phases of matter are described necessarily by symmetry breaking, but it's a large part. For instance, when you melt a crystal, you say, okay, you go from a large entropy, which is maximized in the liquid state, into a low entropy, minimized by the energy. And generically, classical particles like to break symmetry and order at those temperatures. It's actually consistent with the way you understand the third law of thermodynamics, that entropy is zero at low temperatures. So things like to order, like to solidify. But the way to understand it in terms of symmetry is that in a liquid, there are no particular vectors showing any kind of special directions. But once you break symmetry, you have, of course, the lattice vectors, and they're special. So translation and rotation symmetries are broken in the lattice, very known to physicists. Now, you can characterize many phases of matter by the symmetry they break. For instance, charge density waves, which appears in electrons and also in cold atoms and bosons. It's essentially some order parameter, some expectation value of a quantity that the Hamiltonian has a symmetry with respect to, but it spontaneously is non-zero. In this case, you broke two-dimensional symmetry in a charge density wave because there's an amplitude and a phase that you choose. So if you want, you chose essentially a position on the circle. It's called broken O2. That's a way of understanding charge density wave. Magnetism is when you decide that the spins have a preferred direction. They could be ferromagnetic, undergoing, or even other kinds of configurations. But there are special directions they point at that breaks three-dimensional symmetry of three-dimensional vectors. It's called broken O3. Superconductivity, of course, breaks O2 because it has an amplitude and a phase, like in the first case, and you break the phase symmetry of the expectation value of the pair operator. And so you can say that the low temperature physics is marked by which order parameters you have and which symmetries they break. Now, once you broke a continuous symmetry, like O2 and O3 that I showed, there is a theorem. And the theorem says that if you have short-range interactions, that's important actually, the short range, and a continuous symmetry is broken, there exists gapless Goldstone mode of vanishing energy. And we all know the consequence of that in, for instance, solids. In solids, unlike a liquid, you have a phonon, a transverse phonon, that does not exist in the liquid, that has low energy at long wavelengths, vanishes. And it's the Goldstone mode of breaking the translational symmetry of the lattice. So that's the simplest example that you can read. The fact that I knock here and sound travels to there, is a Goldstone's theorem result of the fact that this table broke translational symmetry of the microscopic Hamiltonian. In magnets, you have spin waves. So once the spin points in a certain direction, it can also start precessing. And this theorem tells you that if you break some symmetry, there's going to be some modes, exactly like these, that is going to have vanishing energy. In a superfluid, I'm not talking about the charged superfluid, no, superfluid, but a superfluid without charge, there are phase fluctuations, also at zero energy, on the bottom of this Mexican hash function, Ginzburg-Landau function. However, very interesting things happen at zero temperature because of quantum mechanics. So, you know that the spin operators that represent spins these are now normalized by the size of the spin, so that unit vector operator if you want. So this commutation relation tells you that the commutation relation is non-zero between two different spin directions, and the size of the non-zero commutation goes down when S becomes large and becomes more and more classical. So if you use this to derive the Heisenberg uncertainty principle, you'll see that the fluctuation in X and Y spins is larger than essentially H bar by S, Heisenberg magnetization. So if you have a broken symmetry, it means that there are some quantum fluctuations of this size. So you can see that as S becomes smaller, these fluctuations become larger. What is the consequence of that? Well, it means that if you have some magnetic system at low temperature, you change the size of the spin somehow. But in fact, you can't change the size of the spin, of course, as given to you by the atomic physics. But what you can do is add to the Hamiltonian strong frustration, interactions with fermions, and you also should be in low dimensions. When that happens, even at zero temperature, a magnet can become disordered. You can think of it as the magnet being now in a quantum superposition of spins in many directions.
Antiferromagnet.
It's true that antiferromagnet does that, and the ferromagnet is more difficult to do, but all magnets can be disordered. Ferromagnets, you have to break all three symmetries. Anyway, so you can have a spin liquid coming from all these effects, and spin liquids are very interesting. They're very interesting because they provide for you a many-body interacting ground state that is quite different than the classical product state of ordered spins. Now the question is, what happens in the quantum paramagnet, the non-magnetic ground state? What do the excitations look like? This problem, this is the Heisenberg spin-and-a-half chain, was solved by Bethe in 1931, and even then it was found out that the ground state doesn't break any symmetry. The quantum fluctuations overcome the ordering, and even at t equals 0, there's decaying correlations. If you want, there's a picture of the correlation. There's no long-range order. They decay as 1 over r, essentially. And it's an interesting system, very well studied. And also, the excitations have been found exactly by Beta ansatz. And they look like this. They have zero energy at 0 and pi. And they look like this. This was done by Clouzon and Pearson in 1962. All these facts are known. What is interesting is that when one does spin wave theory as if it had long-range order, it doesn't have long-range order, but if you think it has long-range order, then spin wave theory gives you a curve which is only pi over 2 larger than, pi over 2 smaller than the exact result. So one immediate statement people said, no problem. We don't have Goldstone theorem because there's no broken symmetry, but we have a pseudo-Goldstone theorem. We have nearly broken symmetry, so these are spin waves. And that was the going thought, but that was proved wrong. This is actually a much more complicated system than people thought about. So these are not Goldstone modes without broken symmetry. And the second question people raised is this generic? This was solved for spin-and-a-half. There was no solution for spin 1, spin 2, and so on. Is this property of gapless excitations generic to all spin problems? And the answer was, by most numerical people and experimental and other people who thought about this, yes, it's going to all have these pseudo spin waves in all size spin. Haldane at the time was a postdoc in Grenoble in France, where he wrote an abstract, a paper actually, that had a very interesting history. And in this paper, he actually solved the problem of spin chains in general, spin integer and spin half integer. And this paper, which later was called the Haldane conjecture, and then the Haldane mapping, and then the Haldane theory, it doesn't matter. This paper was rejected by all journals he sent it to. His Rev, the American journals, the English journals, it was rejected. So he sent it around to some friends. He told about it in the conference. I learned it from his talk in the Stockholm. And it was lost. But as he suddenly found out after he was announced the Nobel Prize that Solyom, the physicist in Hungary, kept a copy of the original paper and sent it to him. He took it from the archive, and I urge you to look at it, because when I looked at it, I was surprised. Here he proved essentially what I'm going to show you in a completely different way that I didn't know about, and very nice way, using bosonization, Latinger liquid theory, and some interesting phase interference effect that he found. But as I said, this was only recovered very recently. But I'm going to tell you about the theory itself. The theory itself of integer and half integer spin chains says the following. There are two cases. There's integer spins, where the spin is h bar to h bar and so on, and there's half-odd integer spin, where spin is a half, 3/2, and so on, and there are two completely different cases. Of course, the one that was solved exactly was the spin and half, so it was this case. The integer spin, he claimed, had much stronger disorder than the half integer spin, and there's a gap to all excitations, and the system is incompressible. This was very surprising, because if people believe that the excitations were essentially spin waves, what do you mean to have a gap? What do you mean not to have no spin wave at some low energy? I mean, how can you not have excitations at low energy if you believe that the system is nearly ordered? But this was his result. It's called Haldane conjecture, which annoyed him all the time, because he claimed it was, I think it was quite a rigorous proof what he had. But anyways, that was the result. This integer spin have Haldane gap. The half-odd integer spin have power law decaying correlations, that was known. Gapless excitations, as we've seen before, these decos of Pearson, but could also have enough different ground states in Hamiltonians, which are slightly different, where the system breaks up into singlets. This is a singlet on a bond, and it breaks translational symmetry. So you have some bonds which are singlets and some which are uncorrelated, and that's what I'm doing a Gauss state, and these are the two options. So how did he show it? Well, it was based essentially on a Berry phase, and as you know, Michael Berry, a constant visitor here, a very good friend of ours. There is an interesting quantum effect when you take a spin and you move it on a sphere. So this is a coherent state, which is an eigenstate of the spin operator when you have a magnetic field in the omega direction. And this is the overlaps of the spinors as you go around the circle. And it gives you a phase. And this phase is actually a geometric phase. It's the area, the green area that we have here. And one immediate result of that is if you take and rotate around the great circle, let's say around the equator, you get an area of 2 pi. You get a phase which is 2 pi s, which is minus 1 to the 2s. So it means that there's a big difference between integer and half integer spins. Integer spins, this is always 1. And half integer spins, this will be plus or minus 1. So that's, this could be actually minus 1. But the effects of Berry phase were not really appreciated in many body systems. It was mostly effects of single particle wave functions. And it turns out that these effects are actually responsible for the difference we saw between integer and half-integer spin chains, because it brings interference between histories. It's also important to explain Fermi statistics for spin half or half of integer spins, and it's also a cause of ground state degeneracies in disordered spin systems. So I'll give you a little bit, because this is a colloquium and not a seminar, but as I say, this is a subject of a course, or part of a course in many-body physics. How do you go from an interacting spin model to a field theory? So first of all, you course correct, and you replace the spins with a smooth vector field called N. And then Haldane showed that you can take the Hamiltonian in the path integral and write it essentially as an action, or if you do analytic continuation, as a free energy in one higher dimension. So here is a quantum problem in D dimension. This is a classical problem in D plus 1 dimension. The action is actually an action of a ferromagnet. It's called fancily non-linear sigma model, but it's essentially a vector field with gradient squared interaction. And what's most important is that the temperature of this action, which describes a zero temperature quantum problem, the temperature is finite and depends on the size of the spin. The larger the spin, the lower the temperature. There's a relation. It also depends on frustration and other properties of this J, but this is the most important. So H bar and S appear essentially as a temperature. So if you want to make the system more quantum here, smaller spin, it's like you're raising temperature here. Now that immediately gave a slew of results. In one dimension, the correlations of the two-dimensional ferromagnet decay exponentially with a correlation calculated by Polyakov, which depends on this parameter G. In two dimensions, there's two possibilities. In two dimensions, you know the ferromagnet, in two-dimension quantum goes to three-dimensional classical. Three-dimension has a phase transition, so it means that at low temperatures you can have long-range order. At high temperature, exponentially decaying correlations, and there's transition. And what does this transition mean for the quantum problem? It means the two-dimensional quantum problem can have either an antiferromagnetic ground state with a large spin, or a spin-liquid paramagnet in two dimensions if the spin is small enough and frustration is large enough. So that was the results of this Haldane mapping. But notice a problem. It said that for all spin, the correlations decay exponentially. But before I showed you that for the spin half, it decays like 1 over r. So that was solved by doing the mapping properly and finding that there is an extra Haldane topological phase that has to be added. Now this topological phase is essentially, so in one dimension, this topological phase lives in two dimensions, because as I said, we go to one higher dimension, and it counts in two dimensions how many skyrmions you have. Skyrmion is a configuration of spins, of continuous spins, that wrap around the sphere. So this is the two-dimensional plane. This is my target, the sphere. Every point goes to a point on the sphere. So I can think of writing the mapping as taking the two-dimensional plane, a piece of paper, wrapping around it. I thought actually to do this demonstration, but then I forgot. So anyways, I take this paper, I wrap around the sphere, and now I wrap and I tie it up so that at a large distance, all my paper is on the south pole, and in the center, my paper is on the north pole. And now, you see, I can't get rid of it, because to get rid of the sphere, I need to cut the paper to unwrap the sphere. So this is a topological state, and these skyrmions are configurations that don't cost so much energy. They cost essentially all the J. They exist in the ground state of this model, because the ground state of this model is still at finite temperature, so it has these configurations. But each configuration comes with a sign, either plus or minus 1. So it completely destroys the weight of the path integral, and you cannot really do the mapping that we did before to a classical model when these guys have plus and minus signs. So what is the consequence? If this term doesn't appear, for instance, for integer spin, it's 2 pi times an integer, which is 1, then no effect of topological phase, and we have a Haldane gap. If it's half of the integer, like the beta solution, you get negative sign, that leads to ground state degeneracies, gapless excitation, according to also a theorem by Schultes matrix. So these are the two classes of systems. And the prediction was look for spin 1 chains and look for the Haldane gap. That was something that experimentalists were set up to do. They didn't think to do it before, or when they looked at spin 1 chains, they didn't think they should see a gap there, and they assigned it always to Ising anisotropies and stuff like that. But in fact, the big victory was there is a compound which is very much Heisenberg-like, cesium nickel chloride. It has a sizable gap, and completely explained by this Haldane's gap. The ground state is paramagnetic. It's the typical spin liquid in one dimension. And the spin and a half excitations, as we said before, are gapless because of these topological textures. So that was the work that was done. There was further work that was done on this spin 1 chain. After Kennedy, Lee, and Tasaki wrote Hamiltonian, for which the ground state is exactly known. I wrote the ground state in a figure way. To explain it is the following. Every site has a spin 1, but spin 1 you can always write as a product of 2 spin halves. Now if they align together, it's spin 1, if they're opposite each other, it's spin 0, and vice versa. So you can write the wave function using these dummy spin halves, but you correlate the spin halves on neighbors. It's, the way I write it here is essentially what people do nowadays when they write matrix product states for entanglement purposes, quantum computing, and sorry, Netanel couldn't come, he's an expert on these kind of states. But it's topological. See? Notice why. Because every spin 1 is correlated with one neighbor, and the last one here is not correlated with any neighbor. So effectively, it has a degeneracy. There's a fourfold degeneracy here from the 2 spin halves on both edges. These are localized edge excitations. Now, they're half of the real degree of freedom of spin 1, so they call fractional edge state. It has essentially a moment of spin and a half. So this wave function already exhibits what is later known to call a topological insulator. The bulk is gapped. There's the Haldane gap, I'll show some. The edge is not gapped, and the edge is fractionalized. Why am I so interested in this? Well, in 1988, I was a postdoc in Chicago, and it was very cold in Chicago. I tried to convince Erez Berg not to go there because of the winters there. Suddenly, I applied for a postdoc, and Duncan said, why don't you come and visit? He actually offered me a postdoc, but without money, so. And then he said, why don't you come visit? And I said, sure, I want to come visit. I heard a lot about him from Dan Roberts, who is a disciple of Duncan in a way that, really extreme. So I told Dan, I'm going to San Diego. He said, let me come with you, let me come with you. I said, okay. So we went to San Diego. We rented a small place on the beach there and rented a car, and we used to come every day and talk to Duncan. And a paper came out of that. And the paper was to calculate the correlations in this state using analogy to the fractional quantum Hall effect that, of course, Duncan knew all about. So I'm very proud of that paper, even though I have to admit my contribution to that paper is very small. I essentially sat and looked at both of them running across the board, doing calculations in all kinds of monopole harmonics on spheres, and it was amazing. But anyways, so the story is that this quantum magnetism business grew afterwards and became a big, big business. Thinking about spin liquids not just in one dimension, but what happens in higher dimensions. And then there was another contribution, again topological effects. In higher dimensions, these buried phases I talked about translate instead of skyrmions into hedgehogs, which are configurations that create and annihilate skyrmions. And there was another work that was done by essentially this group, but Ashvin is Duncan's graduate student, so a lot of his wisdom came from a good teacher. And they found that in 2 dimensions, you can have very interesting critical points that are very different than critical points you get in Ginsburg-Landau theory. They're called deconfined quantum criticality, that relate to these topological hedgehogs that appear in the spin-half problem. And there's a whole field of frustrated quantum magnetism, which is looking for spin liquids in 2 dimensions. It's very difficult to find disordered spins in 2 dimensions, because 2 dimensions is a high enough dimension that spins have enough neighbors to order. But if they're small enough and there's frustration, they tend not to. They could not. This is the hedgehog. These are creation and relation of skyrmions. And what Haldane showed in this paper, and was later followed up by Reed and Sachdev, is that when you take an EL state and disorder it by quantum fluctuation, it cannot form a single ground state because of these topological variphases. And it forms 4-fold degenerate, and these are examples of valence bond states that will form that have 4-fold degeneracy. That was a result that was derived there. And frustrated magnets, I want to point out to the colloquium organizer's important work, Matt with Ofer, a paper that never got published, but has more citations than many papers we all have, because it was one of the first papers finding a spin liquid on the Kagome, on Hurwitz-Smithites. This is the data there. It shows that it doesn't order all the way to very low temperatures. And nowadays it has a fancy word for Z2 spin liquid, because it has topological edge excitations. And people are looking at this particular system as one of the few cases of spin liquids in 2 dimensions that can be realized experimentally. Okay, so when I was visiting there, look at the date, 1988, I have the date here. Duncan one evening said, you know, by the way, I wrote this very funny paper on graphene. And I can show that you can get an edge state and a Hall effect without an external magnetic field, without a uniform magnetic field. And this model has electrons hopping on a honeycomb lattice with 2 different phases. And when you solve it, you find edge states, you find the bulk in the center, and the bulk, and it looks like a quantum Hall state without magnetic field. And then I asked him to explain to me the model. He explained to me all these hoppings, and I said, why in the hell would anybody think about a lattice with phases inside the unit cell? And I pushed it aside. And I think he too, because this paper was dormant for many, many years. But it was actually the first paper of topological insulator that later seeded the whole explosion that goes on these days, and probably led to the Nobel Prize that's going on now, and future ones. What was the idea? The idea is that in this model, which is essentially graphene with extra phases, you get essentially a negative mass of a Dirac-like particle, and that has topological consequences and leads to low energy edge excitations. But what is even more interesting is that he thought about a single sheet of graphite. He didn't know that there exists a material called graphene at that time. Many years later, that model that he was thinking about turned out to be realizable by this pair, Gein and Hoffler. They found that they could actually separate sheets of graphene, and they can measure its conductivity, and then the Hall effect on it, and it behaves like Dirac particles in 1 dimension. In 2 dimensions, very big business, which I'm not going to discuss here, but just that he was amused that his toy model suddenly became realizable, at least in one sense. But the biggest thing was that when Kane and Millet and then Schulchen, who talked to Mollenkopf, was an experimentalist, decided to look at a model which is just double Haldane model for spin up and for spin down. And that model is realizable experimentally because that model could be achieved when you have strong spin-orbit coupling. And Schulchen was smart enough to look at the periodic table to find semiconductors that have strong spin-orbit coupling, that this effect could happen, and it happens only if you sandwich it in the right sandwich, and you get these Dirac cones that split in a proper way to leave you with edge states, and that's a topological insulator. So the most important thing about it is that in the center it's supposed to be a gap, it's supposed to be insulating, and all the conductance happens on the edge. And if you don't scatter from spin up to spin down, these are actually good conductors. The experiment showed that the conductivity on the edge is essentially E squared of H, which is what we expect for ballistic transport. And people argue that it's not the cleanest measurement of E squared of H, but it's a log plot. But in a sense, it showed that there are topological effects leading to edge modes, and that's interesting for device purposes. You can channel the conductivity in clever ways, and it started people thinking. Now, the biggest revolution came later when they found, Charlie Kane and Millet found that you can extend this to a three-dimensional band structure. Then the conductance is not on one-dimensional edges, but on the surfaces. And the surfaces of a three-dimensional TI will be these funny metals that cannot be realized in two dimensions. I guess this is a caricature of how the conductance works on these surfaces. These surfaces have very small impurity scattering because impurities don't split the spins. And if you don't flip the spins, the left going don't connect to the right going, and there's no scattering. So a big business came out of all this, and you probably heard a lot about it, and it's been occupying all the conferences and the Nature papers and everything for the last few years. It diverged into looking at metals with topological properties and other systems. Arik Turner is actually very instrumental in the wire metals business. Topological superconductors, which have probably very interesting core excitations called Majoranas. Monty worked on realizing it in photonics, and Netanel works on how to use it to get computations which are protected against dephasing. So all this is ongoing, and it all came out of these simple ideas. So experimentally, it's not just a theoretical field, it's a really experimental field of materials. This is Hassan's paper. These are all arc-based and scanning tunneling microscopy on surfaces. Apparently, a lot of the properties of the surfaces could be detected with these new methods that actually developed for high DC superconductors, and found very useful in these materials. And they discover new materials all the time with better properties. One of the problems is that it's not really insulating in the bulk as much as one would like, but these are things that are having a lot of progress. So that's essentially the story here. So Duncan was here in June, and but because of a conference organized by Erez Netanel and Ehud, took him to the beach, and would meet Yoshua Zad, the inventor of all topological phases in condensed matter. Is he here? Oh, sorry, he's not. Ah, there you are. Okay. He's the one who deserves, and Duncan knows it. So that was a nice coincidence. And here's a picture with Dan. And later we sat down, and he gave me a problem. Now, there was a talk that he gave here once. What? Oh, sorry, 16. Sorry. So when Daniel Podolsky actually introduced him here in a conference, I think it was a few years ago, he said, listen very carefully to this talk, because in 10 years' time, whatever he's telling you now, you might not understand it, which of course was the case. But in 10 years' time, everybody would be working on it. So I take these advice seriously. So he asked me a question about Kubo formulas and conductivity in the lowest lambda level. I was very difficult to concentrate there on the beach. As you can see, you don't see the view that we saw from where we were sitting, so that it was very distracting. But a paper came out of it. Me and Dan actually took his question seriously and managed to answer it. So I'm very happy about that. And the last thing I want to show, oh, sorry, that's it. There is a book that some of you might have seen pieces of it that I've been working on for the last few years. It's about entropy and Maxwell-Demon and so on. And in this book, and for a long time, I've been working on it for 3 years. I actually put a character who's known after that guy. It's called Professor Canonical. And when he got the Nobel Prize, I sent him a present. I sent him one of the first copies of the book. It's not really finished yet. And I thought, oh, I identified my doppelganger. So immediately I went to Wikipedia to see what is doppelganger. Doppelganger is a what is a doppelganger? Caffeine. That's so identified. But don't think that I discriminated against the other Nobel Prize winners, because in the same book you can find 2 graduate students. One of them is called Katie, and the other one is called XY. So, as you can see, Kosterlitz and Thales and the XY model are well represented there too. So, okay, thank you very much.
Okay, questions? Sure.
To start with a remark, I think when there's a conference on the 60th birthday, Haldane was here, and I think you mentioned to me that he might be getting a Nobel Prize soon, but it was quite some time ago. And now the question is,
when will you get one?
You talked about topological isolators, and then we talk about the phase of matter. And you also mentioned Berry's phase, which is the phase of the wave function. Is there any connection between these phases?
Well, he used Berry phases to characterize the spin integer and half integer phases of matter. So essentially he was using Berry phases because Berry phases appear in the partition function in quantum problems, not in classical problems. And they separate cases where they're non-zero. So because half integer spins give you minus signs from these Berry phases, the physics is completely different. The excitation spectrum, the ground state is very different because of the Berry phases. Now, I should mention that in his Nobel talk that I listened to, he mentioned the Berry phases, and he said, by the way, he was kind of pointing at some of the committee, you should think of Berry as the next guy to get a Nobel Prize, and he was very generous about that. So I think, yeah, he used these things a lot.
But Berry phase appeared on the market in '83. But you were saying that Haldane was using it in '81 in his rejected paper.
Good observation. That rejected paper was the previous paper which he didn't use Berry phases. He used Latinger. Okay, I just said it's 2 words. He used Latinger theory, and he noticed that you cannot put cosine. There's cosine m phi that goes into the Latinger theory, but m has to be for integer spin. It could be anything, but for half integer spin, it has to be multiples of 2 pi because of the rotation of a spin by 2 pi gives you a minus sign, and you don't allow that in the partition function. It's a restriction on m, and once you put that restriction, you get a big difference because the half integer spin, the cosine phi is irrelevant and it's completely algebraic, and the other one gets a gap. So he made all his claims correctly, but he did use Berry phase only the fact that rotating a spin and a half by 2 pi gives you a minus sign. That's what I learned from reading that paper. I never knew about that paper. As I said, it was hidden for many years. Yeah.
What is missing in the classical examples of topological, mechanical topological stuff? What is missing in the classical system?
Phases. The phases, because the topological stuff.
So just the word topological is to.
No, topological is usually a sign of some stability, right? because integers can't change continuously.
Yeah, but you get edge effects also in classical systems, classical mechanics.
Yeah, but I'm not sure, okay, about classical mechanics, Yossi knows much more than me, but I think that,
Not quantum too.
quantum two, yeah, that's right. That's kind of nice, right? So I think that it's very different there. I mean, there you ask about energy, just energy, and its stability for different configurations. You know, vortex is stable classically because you can't get rid of it, right? But in quantum mechanics, you look in wave functions at different contributions, and topological phases just eliminate certain contributions from the wave function. So it's a different effect. It's purely quantum. Yeah.
I have a question. So now in the lab of Ophir, they actually see skirmions.
Yes.
Is anything from that story relevant to the skirmions that they see?
There is a lot of interest in transport of electrons through skirmions. And that is relevant because there you also have Berry phases. And you can show that if you take electrons and you let them flow through a skirmion background, it looks to them as if they are flowing in a magnetic background because they feel the gauge field of the spin of the skirmions through their Berry phase, through the overlaps of their wave function. So that I think it's very interesting to have configurations. We have topological densities called topological numbers. They would lead to transport effects and the others.
No more questions, so if that's the case, let's thank Assa.